Hello everyone. So as I mentioned in class, we're going to start to do some recorded lectures. That way you can get some more content and also be able to watch it at your own pace and your own speed. So we're going to start our first one off. This one takes about 25 minutes or so. So again, I'm really encouraging you to continue to look at the slides that are already online and make sure that you're recording, you're taking notes on this material. And then I'm going to give you opportunity in class to discuss any questions. So as we start talking about metabolism, we really need to set a platform of what energy is. So we're going to be talking about that, which is in chapter 6 of your book. All right. So again, I'm going to talk a little bit about chemical reactions and kind of remind you about what we talked about. But we're going to spend a majority of our time talking about these different energy types, which I know you've heard of before. And as I talk about them, hopefully they're a bit familiar. We're also going to talk about the laws of thermodynamics and how energy is able to move as far as if it's an exergonic reaction or endergonic reaction. And finally, we're going to touch just a bit on ATP, which we've already discussed a little bit in class. All right, so this is just kind of something to get your brains thinking. So this is an image of the Olympics, and the gentleman in the front, if you didn't know, that's Usain Bolt. He's one of the fastest people in the world. So the riddle is, what determines if Usain Bolt will win a race and if a chemical reaction will occur? So on the right, you see a chemical reaction with some reactants on the left side, some products on the right. So between the two, what are the things that need to happen for both of them to occur? Give you a second. You guessed it, direction and rate. So the same way if you're in a foot race, you have to run in the right direction. We see that all the time with little kids playing pee-wee football. They go the wrong way, but you have to go the right way. So that direction is number one. And then secondly, it's the rate. So everyone behind Usain Bolt, they're going the right direction, but the rate is off. So that same thing happens with chemical reactions. Our direction has to go from reactants on the left side to the products, and also has to be able to go at a rate that's acceptable. So we need to start talking about energies and rates and how this occurs realistically. So we know a lot of chemical reactions occur frequently in the body. We've already talked about our macromolecules and how to build and break those down. But if you're thinking about any type of chemical reaction, what is the thing that they need to be able to occur? Energy, right? We all need energy to be able to move about and to do the things we're doing, which is essentially just being able to use those chemical reactions happening. So let's talk a bit about energy. So this is going to be your textbook definition. If you are a flashcard fan, this will be a great thing for a flashcard. So energy is defined as the ability to produce change or do work. So if you think of something that has energy, we'll talk a lot about the change method, but even work, right? If you're feeling like you don't have enough energy or you're not energetic, that means you're kind of down and kind of mellow, you're not doing too much. So the ability to promote change or do work is the definition of energy. Secondly, energy is measured in this funny looking word here, which is pronounced joules. So just like diamond or rubies, joules, energy can be measured in joules. And there's different types of energy, and I'm going to briefly talk about those. So before we start going into this slide too much, I do want to point out this area here, which tells you that you only have to recognize the names. So again, a multiple choice question or maybe short answer where I ask you to tell me, 2 out of the 5 names of the energy we have biologically. I only need you to remember the words that are in the color and the bold lines here. So just kind of note that down. So I'm going to save mechanical energy for last. We're going to start here with chemical energy. Chemical energy is energy found between chemical bonds. So all the food we eat has chemical energy, and I'll show you an image. And then also some of the energy associated with maybe fossil fuels or oil. That's all chemical energy. Secondly, we have thermal energy, and this is energy that occurs when molecules are moving at a very fast rate. And by them moving at a fast rate, it creates this type of heat. and that heat can be able to give off energy. Nuclear energy, we don't talk about too much in an everyday basis, but it's a really important form of energy in which you're looking at the nucleus of your atom. So if you remember, your nucleus contains your protons and neutrons, good. And because the protons and neutrons are there, if we break them apart or if we add them together at a certain rate and in the right direction, we can create some energy as well. And then what we're used to in most our everyday lives, electromagnetic energy. And this is where you have energy between magnets and electricity. So a lot of our light waves, microwaves, UV waves, X-rays, visible light, all this is associated with electromagnetic energy. And finally, the one we focus on is mechanical energy. So if you hear something associated with mechanics or mechanical in nature, it's essentially something that has to do with movement or the process of movement. So we're going to talk a lot about these two forms, kinetic energy and potential energy. So within mechanical energy, so if you're writing a chart, you would write mechanical energy up top, and then you would follow it with under mechanical energy. There are two types, kinetic and potential. So with kinetic energy, it's energy associated with movement. So anytime something is actually happening or occurring or in action, this is kinetic energy. So if you're walking down the street, if you're eating a sandwich, if you're riding your bike, all of these things are kinetic energy because they're associated with movement. It's actually something that is currently happening at the moment. So the energy that you have when something is currently happening. The kind of the opposite, or the other one that's associated with mechanical energy, is called potential energy. So we all know what potential means. If something is potential, that means it's likely to occur, right? It's potentially going to rain today. That means there's a high chance that it's going to rain. So if this is potential energy, this is an energy that a substance or molecule has due to its location. So I'm going to explain what that means in just a second, but it's potential energy. It's due to energy of a location. So it is thought of as potentially occurring. So where it's located at, it's probably going to happen very soon, or stored energy. So I'm going to give you some good examples, but think about a rock at the top of a hill. So if it's sitting at the very peak of the hill, then it has potential energy because the location of where it's at, the top of the hill, suggests that it's going to start to give off kinetic energy soon. So think of something that has potential energy as giving off kinetic energy soon or next. So potential energy typically happens first, and then kinetic energy happens afterwards. So looking at this image here, this is a gentleman shooting a bow and arrow. And as you see here, in this picture, he has the arrow pulled back in the bow. It's about to be launched. And then the image to the right, he actually let go of the arrow and it's moving. So if you had to look at option on the left or the option on the right, which one will be kinetic and which one will be potential? Great. Hopefully you said the one on the left is potential. Do you see the location of the arrow? That means that once he lets go, because of the arrow being at the location of being pulled back, once he lets go, that arrow is going to move. So it's potentially occurring or stored energy. That's here on the left. On the right, the arrow is moving. So you see in this, of course, it's a still picture, but if you're looking at the arrow in motion, excuse me, it's actually moving, so that would be kinetic. Okay, spoiler alert. LeBron James. So this is a picture of LeBron James, if you didn't know. And he's holding the basketball. He's holding the basketball in a shooting position. So looking at this image, let's say this is him right now. He hasn't shot the ball. He's just holding the ball in that position. What type of energy would this be? Potential or kinetic? Ding, ding, ding. I hope you said potential. because the ball is not moving, because the location of the ball, it suggests that eventually it's going to start moving. So it has a stored energy. Nothing's happened yet, but because the ball is in a shooting position, because the ball is in a location that makes it likely to move soon, this is potential energy. All right, so for our roller coaster fans, if you're riding a roller coaster and let's say you're sitting at the top, roller coasters sit for about 4 or 5 seconds, just enough time for you to wish you weren't on the roller coaster. If it's sitting there for 4 or 5 seconds, what type of energy would that be? Potential or kinetic? Potential. You see the location is at the very, very top. So it's not moving in this picture. Let's say it's not moving. It's not moving and the picture is sitting at the top, but we know it's going to potentially start to move soon. And when it does, it's going to release some energy. So let's say you went down the roller coaster and you're holding on for dear life. The roller coaster is in motion. Is this potential or kinetic? Kinetic, that's the answer. So kinetic is anything moving. So you see here, you can visibly see that there's some motion. So that's going to be kinetic energy. And then finally, the last image we'll look at, this is you on a ski slope sitting at the very, very top before you move down the slope. What is that? Potential, very good. So you have not moved yet, but the location of you being very high and being able to almost come down the ski slope suggests that there's going to be some energy occurring. So great job with that. To kind of wrap up the potential and kinetic energy, if you're looking at chemicals, right? So let's say this is this is H2O, and we know between H2O is a polar covalent molecule, so you see some of the covalent bonds there. If you break apart a covalent bond, it has the ability to release energy. So what that means is that covalent bonds have what we call chemical potential energy. So that just means potential, right? It hasn't occurred. And once we break apart this bond, we're going to release energy. So it's called chemical potential energy because we have not released it yet. But once we break apart these bonds, we know energy is going to be released. Okay, so this is the first portion of the lecture. So if you've got to this point, I would really suggest you go back and rewind areas that are challenging, or make sure that you're taking notes just to make sure you understand all of this before we go to the next part. If you're totally fine, then we can continue moving. Okay, so thermodynamics. Thermodynamics is another flip card word you can use, or flashcard word. And thermodynamics is the study of energy transfers. So we just talked all about what energy means and the different types of energy. But when we talk about energy going from one form to the next, this transfer of energy is called thermodynamics. There are 2 laws of thermodynamics, or at least 2 that we discussed in this class. The first one, I'm sure you've heard of it before, and that is energy cannot be created or destroyed. So all energy, we cannot create new energy, and we cannot destroy any energy. It just has to be transferred from one form to the next. So if you look at this image here, this is showing a solid color block, which is supposed to represent our energy. It goes through some type of transformation, and now it's a striped block, but it still weighs the same. You haven't gained any energy, you haven't lost any energy. It's all there because we cannot create energy or we cannot destroy it. So the first one is pretty simple. And to follow up with that, if you're wondering where the energy goes, the energy is essentially just transferred. We're just taking it from form A to form B. That's all that happens with our energy. So this is just an example showing that we're not losing any energy or gaining any energy. We are just transferring it. So if you filled up your car with gasoline, let's say we're talking about 100 units of chemical energy, you're going to have a chemical reaction. That will be you turning your car on and your car doing the car thing it does. And what you have is 75 units of heat energy that's going to be given out from your exhaust, and 25 units of kinetic energy, which is how your car's wheels turn and how it moves. So if you're looking at the numbers, you still start off with 100 on the left side, and you still end up with 100, whether it's the 75 plus 25 on this side, but you're just transferring the form. So instead of it being a liquid form of gas, it's now this heat and also this kinetic energy that you have. Okay, so this is an image here, but I'm not going to really discuss it. But essentially, it was trying to discuss how energy is transferred from the cold ice cubes into the warm lemonade. But I can explain that in class if anyone wants to learn more about that. Okay, so the second law of thermodynamics, this says that any energy transfer, what this one is saying is that as we go from one form of energy to the next, is going to create chaos. It's going to create disorder. The word we use to describe chaos or disorder is this funny word here, which is called entropy. So entropy. So anytime we go from one form of energy to another form, it's going to become more chaotic, more movement, and that is called entropy. So if you see here in this picture, let's say you have this nice little ball of energy molecules, and you're going from, let's say this is a solid to a gas perhaps, it's going to cause more disorder. So you see the particles are really spread out. It causes them to move around a lot because every time you transfer energy, again, we don't lose any or we don't gain any, but it is much less organized as we transfer between each state. So any energy transfer from one form to the next increases this entropy. So the more time we transfer energy, the more movement you're going to have, and that more movement is going to lead to more disorder or more instability. So as you move and change energy over and over and over, it allows your molecules to be a lot more unstable, which can be a good thing or a bad thing depending on what you're talking about. So an example, if you think of an ice cube going from a very solid core of ice and melting, which is just energy transfer going from into a cooler temperature, you're going to see the liquid, visibly it actually spreads out. So it's going to go from something here, which is a solid and really organized, to something really, spread out and relaxed like a liquid. And that's going to be that increase in entropy. So again, this is just showing a gas. The same thing happens here, but I really wouldn't worry about this line. I'm not going to ask you about it specifically, more focused on what the law is trying to say. Technical difficulties here. All right, so this is a picture of these adorable kids. Anybody that's around kids, you know how if you go to their playroom and clean it all up, it's very nice and organized. So think of this as your energy form number one. Things are together, but over time, things get really messed up. So the more movement of these kids, the more chaos that you have. So again, every single time you have movement, you're going to increase the chaos. So right here, everything is calm, everybody's happy. More movement is going to increase that chaos. So this is just another visual example. Okay, this is in your notes, but we're not going to talk about it, so we're just going to move forward. Now this area is probably a little bit more challenging, but I'm going to work through it as best as possible here, and then if you have questions, we can talk about it in class. Again, make sure you're rewinding and trying to understand if it still becomes challenging. Okay, so with any reaction we have, it can basically fall into two categories. One is an exergonic reaction, exergonic, and the other one is an endergonic reaction, endergonic. And I'm going to go through each one. The first one is exergonic. You see the EX at the beginning is green, and I'm going to tell you why I made it green. Exergonic reactions are spontaneous. So these are things that happen without you trying, right? So for instance, acetone will evaporate if you just let it sit out. So spontaneously, without us telling acetone to evaporate or without us having to heat it up, it naturally will spontaneously evaporate. So anytime you have an exergonic reaction, it is spontaneous. It occurs without any type of help. There's a term called delta G, which we won't dive into, but I do want to make sure that I mention that reactions that are exergonic or reactions that are spontaneous always have a negative delta G. So if the question says you're looking at a reaction that is spontaneous and has a delta G of negative 45, what type of reaction would it be? It would be exergonic because that delta G is negative and it's spontaneous. One really critical thing about this, which highlights the green area, is exergonic reactions are spontaneous because energy is released by the reaction. So energy will exit. Do you see how EX starts with exit starts with EX, and so does exergonic? So when you're thinking about energy being naturally released from the reaction, this occurs in exergonic. So exergonic reactions are spontaneous, they have a negative delta G, and energy exits. That's your tagline. The opposite is endergonic reaction. Endergonic reactions are not spontaneous. We have to do something to get this reaction to occur. So it's like if you put gasoline in your car, which is energy, you still have to combust turn the engine on, get everything moving and going before the car moves, right? It's not spontaneous. You don't put gas in and the car just moves by itself. So an endergonic reaction is exactly the opposite as exergonic, meaning it has a positive delta G. So another question can say, you're looking at a reaction that is not spontaneous with the delta G of positive 45. What type of reaction would this be? Endergonic. And you see the EN is green because this reaction requires energy to be able to occur, meaning energy enters. So that's really critical to keep in mind. If you don't remember anything else, remember exergonic reactions, energy has to exit or leave the reaction. Endergonic reactions, energy has to enter or come into the reaction before it actually occurs. So this is just an image showing that here. Remember, exergonic energy has to do what? Exit. It has to leave. So A plus B is going to equal C plus the energy that left. Okay? And if we're talking about delta G in this picture, if you're looking at the scale, you see the delta G goes down, so it's actually negative in this reaction. And the opposite is endergonic, in which energy has to enter. So A plus B plus the energy that entered equals C. And if you looked at delta G, it would also be positive in this particular case. So between this slide and the previous slide, please make sure you recognize the equations and also being able to recognize energy, the movement of energy. Is it going to enter? Is it going to exit? Is it spontaneous or is it not spontaneous? So again, take some time to reflect on that because that's probably the most challenging thing from this recorded lecture. However, we can definitely go through it in class to make sure everyone's on the same page. Okay, the last few slides just talk about ATP, which we've already talked about a lot, but I wanted to make sure I gave you some formal training on it. So ATP, which we call belovingly, actually stands for adenosine triphosphate. So you see the A, the T, and the P. And ATP is the major mediator for driving cellular processes. So if you look at the structure of ATP, we have a nitrogenous base, we have a 5-carbon sugar, and we have a phosphate group. Do you remember which macromolecule has these components in them? Nucleic acids. So if you remember, adenine is one of our nucleic acids. That's a kind of a hint right there. But our nucleic acids is the macromolecule that ATP is, and the monomer of a nucleic acid is a nucleotide. So that's what the adenine is. Okay, so we also talked about ATP being produced, and ATP is being produced in the mitochondria of the cell. So we always talked about the mitochondria as the powerhouse, and this section really dives into what does it mean for it to be the powerhouse and how does that work in particular. Okay, a really important thing about this is remember the T of ATP. It stands for triphosphate. So if we look in this image here, this is a molecule of ATP, and you see it has 1, 2, 3 phosphate groups, making it a triphosphate. So the great thing about ATP is if we perform hydrolysis, do you remember that? It's where we add water in, hydrolysis, water breaking. We can add that in to break up our ATP molecule. It actually takes it from ATP, triphosphate, to ADP, diphosphate, so 1, 2, and then also an extra phosphate group. So make sure you rewind that if that's a little bit confusing. But ATP is really special because it can go back and forth. So it can go from a triphosphate where you have 3 phosphate groups. You can add some water in, break it up, and then you have 2 phosphate groups plus your other phosphate that's hanging around. So if you look on this equation up here on the top left, you see you still have 3 phosphates here on the left side, triphosphate, and on the right side you have 2 plus 1, so you're not losing any of your phosphates, you're just changing the format of that. And finally, kind of summarizing everything we've talked about today, this is showing that ATP actually can link together endergonic, energy has to enter, and exergonic, energy has to exit reactions, because ATP, when it's in the triphosphate stage, once it breaks down, that breaking down of ATP to go to ADP is going to actually release energy. So it is going to be an endergonic reaction. And then as you go from ADP and bring it back to ATP, that's going to be an exergonic reaction. It's going to be able to release energy as well when we bring those bonds together. So I hope this was a useful lecture for you. We're going to see how this works, and if there's any questions, please let me know. I definitely want to make sure that I can answer questions for you. And we'll talk about this lecture in class a little bit to make sure there's anything that you need. And good luck. All right, bye.